We will start this new video talking a little bit about history, in this case American history. In the previous videos we have talked about how the criteria for spontaneity, the criteria for things that are going to happen is that the entropy of the universe, right, if you think the system and the surroundings, that the entropy change has always have to be zero. However, there is no limitations as for if the entropy of your system is going to be positive or negative. In both cases can happen. What the second law of thermodynamics in terms of the entropy says that the entropy of the whole system plus the surroundings have to be larger than zero. This is why entropy is somewhat deficient in the sense of trying to understand if a process is going to happen when we study a specific system, because the entropy of the system can be positive or negative. We will introduce the change in Gibbs free energy, and this new variable is named after one of the most important, definitely one of the first important American scientists, Josiah Willard Gibbs, who reformulated in so many ways or created the field of thermodynamics at the end of the 19th century. Almost all by himself, almost in isolation in the United States when most of the science was happening in Europe. So we will try to explain why the need for this new variable is needed for spontaneity and why it's not convenient to keep using entropy to decide if a reaction or a change is going to move forward or not. So let's study, for example, these three cases, and we will see how entropy changes in these four cases. Again, the change in the entropy of the universe has to be positive. However, nothing says about if the system can be positive or negative. As long as the surroundings is large enough, that makes the two summation larger than zero. So when oxygen dissolves in blood, you know that because you go from gas to dissolved in liquid, the entropy of the system has to be negative. This means, of course, because the second law of thermodynamics is always positive, that the entropy of the surroundings has to be positive, and positive enough so that when you add this up, these two terms, the summation is positive. How can one make the entropy of the surroundings positive? How can one increase the disorder of the surroundings? Well, by kicking out heat, so by losing heat. In other words, it means that in the system, when oxygen dissolves in blood, the enthalpy has to be negative. That is, it has to be exothermic. There has to be some heat coming out of the system that goes into the surroundings that makes the entropy of the surroundings increase. We are warming up the surroundings, therefore the entropy of those surroundings increase such that the entropy of the universe is still positive. Because oxygen does dissolve in blood, that's something that happens, therefore the entropy of the universe should be positive. Another example, when water liquid evaporates into vapor. In this case, you're going from liquid to vapor. The entropy of your system is positive. The system increases in disorder. However, the enthalpy, we know that one needs to provide some heat to evaporate, therefore it's endothermic. Okay, so this means that probably the entropy of the surroundings, because we are removing heat from the surroundings because the system is exothermic, the change is exothermic, this will probably be negative. Last one, hydrogen and oxygen react to make water. If you see, we have 1.5 molecules become one. The entropy in this of your system should be negative because you go from 1.5 molecules to just one. You decrease the number of molecules, the entropy of the system should be negative. This means that for the second law of thermodynamics to be true, the entropy of the surroundings has to be positive, and more positive than negative the entropy of the change in entropy of the system is, so that again the whole entropy of the universe is positive. So how can one increase the entropy of the surroundings? By kicking out heat. In other words, this reaction is actually fairly explosive. It releases a lot of heat, and this is the main driving force that takes place. And finally, carbon dioxide and water gives glucose, and oxygen. And if I'm not mistaken, I think there's a 6 in here. I would have to check. I think these are all 6. Now, notice you go from 12 molecules to 7. The entropy of the system is negative. And this reaction would not work and if it weren't for the fact that one needs to add, I put the energy of a photon. The plants use the solar energy to move this reaction forward. Therefore, it has to be that the entropy of the surroundings is positive. Therefore, it can only be positive when your reaction, when your system is kicking out heat. If it kicks out heat to warm up the surroundings, it's because the enthalpy of the system is negative. It's exothermic. So notice that there is a relationship between the entropy of the system and the enthalpy of the system. There has to be something that compensates the decrease in disorder of your system, and that's typically kicking out heat. So let me rephrase that in a different way. One can reformulate the second law of thermodynamics as by particles spreading out, and that's how we measured the entropy. When particles spread out, the disorder increases. This means that the entropy is positive. But we have seen also that in some cases, even though, like in this case, when you have a condensation, or maybe that's a liquid becoming solid, whatever, but there's definitely particles do not spread out, but there is a kick out of energy. The process is exothermic, so that what it does, it increases the entropy of the surroundings, so that at least the overall entropy of the universe is always positive. What we're trying to say here is that one can reformulate the second law of thermodynamics either by thinking particles need to spread out or energy needs to spread out. In other words, heat needs to be kicked out. Either you want an exothermic process or a highly entropic or entropically favorable process. These two principles, the principles of minimum energy, in which case a system tends to kick out heat or energy, or the principle of maximum entropy, can be understood in one single property, minimizing the enthalpy or maximizing the entropy. And that's what the Gibbs free energy will give you. The Gibbs free energy is still the second law of thermodynamics, but includes these two principles in which you want to either minimize the energy or maximize the disorder. In both cases count for the increase of entropy of the universe. So this is pretty much what the Gibbs free energy is for. In a way, you can think of it as useful energy. We would need more time to really explain that. But another way to understand Gibbs free energy is think of it as if it were a chemical potential. If you've taken physics and you have seen electrical potential or gravitational potential, it means that the lowest your potential is, the better. So when you think you have a reactant and two product, and there is a decay in chemical potential, so it would mean final minus initial, that is negative, that is something that is going to happen. So this is the criteria. When the change in Gibbs free energy is negative, that is you're going to see a forward process. When the change in Gibbs free energy is positive, that will be for a reverse process. And when the Gibbs free energy change is zero, it means that, at least macroscopically, nothing will move. We call this equilibrium. In equilibrium, there is no motivation to macroscopically change the the proportions of reactants and products. This is the new variable that we will use. We have reformulated the second law of thermodynamics, and we will keep using. Notice that in this case it depends on the temperature. There is not much time to actually demonstrate this equation, but if you take a physical chemistry course, there'll be time for that. But in the way you should read this new second law of thermodynamics formulation is that we are seeking either to minimize the enthalpy, that is the principle of lowest energy, or maximizing the entropy, that is the principle of spreading as many particles as possible.